My name is Aaron Clausen. I'm one of the computer science instructors here at Western Washington University, and we've started to take these video lectures to bring our computer science topics to the larger community. This was a project invented by Sean Basler, who is also our cameraman, editor, and quite frankly, every other role in producing these videos. Today, we're going to talk about the IEEE 754 specification, and this actually defines a bunch of data types for floating point values. Specifically today, we're going to talk about the single precision float type. This spec also defines a double precision and, believe it or not, a half precision type. But let's just stick with a 32-bit float. Floating point types are the computer science equivalent of scientific notation. So from an intuitive standpoint, if I have minus 5.337 times 10 to the second, what this really means is the number minus 533.7. The 2 here says move the decimal place 2 places to the right. This intuition applies in binary. So I could have the number 1.101 times 2 to the third. Our 10 gets replaced with a 2 because we're in binary. Our digits here are all 0 or 1, and we now have this binary point. What this really means is, again, we move the binary point 3 spaces to the right, and this is really the integer 13. 8 plus 4 plus 1. But what we want to do is encode this and preserve this scientific notation structure. And just to be complete, this is positive 1.101 times 2 to the third. Well, there's 3 pieces of information I need to keep track of. This plus sign, for sure, the exponent, and then actually just these fractional bits. The reason why I don't need to encode this 1 is just like in base 10 scientific notation, the digit that comes before the point can't be a 0, if not you'd shift things around. It has to be some other value. Well, in base 2 our only other value is a 1, and so I don't need to encode that in our format. I can just let it be implied. So here's the format. I need 1 bit to encode the sign. This is actually asking the question, is the value negative? In our case, it's positive, so it's not negative, and I encode a 0. I need to encode this exponent. I have 8 bits of exponent. This is not a 2's complement number like you're probably used to. This is actually biased by 127. Which means I put the bit pattern for 127 in there to indicate an exponent of 0. Well, I actually want to encode the exponent 3. So I would take 127 and add 3, which would give me 130. And then I could encode that in binary and put that there. That's actually a little complicated. I find this easier. If I take 127, which has that bit encoding, and I add 3. 1 plus 1 is 2, which gives me a carry. This is a 3 and a carry. A 2, 2, 2, 2, and a 1. This is actually the bit pattern I want to encode here for a positive 3 exponent. If you notice, it's actually 1 less plus that 1. And that's sort of a quick trick to take a positive exponent and encode it is you subtract 1 and just remember that the most significant bit is going to be set. There's my plus 3 as the exponent. After that I have the fraction. Well, this is a 32-bit number. I've used 1 for the sign, which gives me 31 bits. I've used 8 for the exponent. I've got 23 left over. I have 23 bits of fraction. Well, remember, I don't need to encode this 1. It's sort of have implied right there. I just need this 1, 0, 1. So 1, 0, 1, 0, 0, 1, 0, 1 plus 23 zeros encodes this value 13. So let's work through an example. Let's encode 3/16. Now there's a couple of ways to encode 3/16 into that binary scientific notation. One is very intuitive. Well, 3/16 is going to be 3. And if I put the binary point there, it's going to be 3. There, it's going to be 1.5. There, it's going to be 3/4. There, it's going to be 3/8. And there, it's going to be 3/16. So intuitively, that's the value we want to figure out. But here's the algorithm to actually do it for any fraction. The first question you want to ask, are there any 1s? Is this value bigger than 1? And then you just go through the normal base 10 to base 2 conversion. In this case, there isn't. I have 0 1s. And now I want to ask the question, are there any halves? Well, we could think about this, or what we'll do is multiply it by 2, and if there are any halves in there, it will become greater than 1. So 3/16 times 2 is going to be 6/16, and we can right away see that there are no whole values in there. It's less than 1, so we put down 0. And then we continue. 6 times 2 is 12, so we have 12/16, still smaller than 1. 12 times 2 is 24. 24/16 is larger than 1. We're going to account for that 1 there, so we have to subtract it off from here. And what I end up with is 1 8/16. That's the one that gets taken care of. So since the 1's taken care of, I just double the 8/16 and end up with 16/16, which is exactly 1. That gives me that one. I have no 16ths left over, so I can just write down as many zeros as I want. And if you notice, that's the same value we expected intuitively. But now we need to encode this into our floating point standard. And what we need to do first is move this binary point 1, 2, 3 spaces to the right. So we end up with 1.1 times 2. I made this number bigger. I've got to make this number smaller to the -3. So, to be complete, we have our plus sign. And then here are the parts I want to encode. The plus sign, the fraction, and all of the following zeros, and that exponent. So if we remember, our sign bit answers the question, is it negative? It's positive, so that's a 0. Our exponent is biased by 127, but now I'm subtracting off 3 rather than adding 3. So I take my bit pattern and I subtract off 3. If you notice, all I've done is turn those bits off, the bits that represent the 3. It's a little trick to encode a negative number quickly. So this is my exponent. And then my 23 bits of fraction. The 1 is implied, so it's really just 1 followed by 22 zeros. And that is the encoding of 3/16. Let's convert the value 7 1/3 into binary. And our first step is to convert this into the binary scientific notation. So right away I see that we have 7 whole numbers in there. So I can encode 7 with 111 and my binary point. And now I'm just going to work on the third since the 7 is already accounted for. And I have to ask the question, are there any halves in there? And I'm going to do that by multiplying a third by 2. So I end up with 2/3, which is smaller than 1, so there are no halves. I'm going to multiply it again by 2 to ask the question about quarters. And I end up with 1 1/3. 1/3 or 4/3, which gives me a 1. So I'm accounting for that 1. And now this repeats. Multiply by 2, I get 2/3, which gives me a 0. I multiply this again, which gives me 1/3, which gives me a 1. And this pattern actually just repeats over and over until we run out of ink. So to put this into scientific notation, I need to actually move this binary point over here. So it would be 1.110101, and I'm going to put a bar over that just to indicate that it repeats forever, times 2 to the, well, I've made this number bigger. I'm sorry, I've made this number smaller, so I have to make this number bigger. So I moved it 1 to 2 places. This would be 1.110101 times 2 to the 2. So now when we encode this, again, this is a positive number. So my sign bit is going to be a 0 because it's not negative. My exponent is going to encode +2. But remember, this is biased by 127. So I take 127 and I add 2. But we've already seen a trick for this. So really what I need to do is encode a 1 with the most significant bit 7. It's an exercise to the viewer to actually go through and check my math. And then I need to encode the fraction. And I've got 23 bits here to encode, and I don't need to encode this part, just that part. So it would be 11010101 out to 23 bits. This is the floating point encoding for 7/3. I'm sorry, 7 1/3. So let's convert a number from the representation into the base 10 value. So if we take the encoding 0, 0, 1, 1, 1, 1, 0, 1, 1, 0, 1, 0, 1, 0, 0, out to 32 bits. This is going to be a floating point value, and we can break up the bits into a sign, an exponent, 23 bits of fraction. So we know right away that this is going to be a positive number because our sign bit is 0. It's going to be 1 point the fraction, 0, 1, 0, 1, 0, 0, 0, however far we'd like to go, times 2 to some exponent. Well, right away we can see that this exponent is going to be negative because this bit pattern is less than 127. And this is why we want to use that trick. Since this is a negative value, what I did is I turned the bit to a 0 for the 1 in the case of the positive exponent. So for example, this is actually times 2 to the 4th, times 2 to the negative 4th. And we can actually check our work. So if I take 127 and subtract off 4, what I'm going to end up with is the bit pattern we're working with. So we could go to a scientific notation, from our scientific notation, get rid of this times 2 to the minus 4, and move our binary point over here to the left. And what we would end up with is 0.000, the 3 places, the 1, which is this one, 0, 1, 0, 1, 0, 0, 0, and I don't need the times 2 anymore, but this is kind of awkward to work with. Alternatively, I'm going to move this binary point to here. 1, 2, 3, 4 places to the right. I'm making this number bigger, so I've got to make that number smaller. I end up with 1, 0, 1, 0, 1 times 2 to the minus 4th minus another 4. This is now a fraction. So this is actually the number 21. divided by 2 to the 8th. Well, 2 to the 8th, 2, 4, 6, 8, sorry, 2, 4, 8, 16, 32, 64, 128, 256. This encoding is actually encoding the value positive 21 256.